integrating square root x ln x over x squared plus 1 between 0 and infinity. Okay, so first I want you to consider the following parameterization. So you have I of a equals the integral between 0 and infinity of x to the a over 1 plus x squared. Okay, now let's see what happens if we take the derivative of both sides with respect to a. So what we end up getting is I prime a is equal to the integral between 0 and infinity. Now differentiating this with respect to a, so you see 1 plus x squared is just a constant because we're differentiating with respect to a here, and x to the a differentiates to x to the a times ln of x because x is the base here. And what you might notice is that if we plug in a equals a half, then we end up getting the original integral. So that's what I want to do. We want to, first, we're going to want to find IA, and then we're going to differentiate the result and plug in a equals a half. And that's how we solve the problem. So let's get started. So we wanted to integrate IA. Integral between 0 and infinity of x to the a over 1 plus x squared dx. So we're going to start by making a u substitution of u equals x squared, du equals 2x dx. So now we have IA equals a half. Now the limits here are going to stay the same between 0 and infinity. X to the a will become u to the power of a over 2, and on the bottom we'll have 1 plus u. And from the substitution, this is multiplied by 1 over x is going to be the square root of u, which we will write as u to the half. So now this is what we're working with. But now, watch what happens when we bring that u to the half to the numerator. So we have u to the power of a over 2 minus a half over 1 plus u. Oops, 1 plus u du. And you'll notice that this is actually our best friend, the beta function. So the beta function of mn can be written as the integral between 0 and infinity of t to the m minus 1 over 1 plus t to the power of m plus n dt. And you can see here that this integral is in that same form, where a over 2 minus a half is m minus 1, and 1 is just m plus n. So let's see what we have here. So we have m minus 1 equals a over 2 minus a half. So we can say m equals a over 2 plus a half. We have m plus n equals 1. So n equals 1 minus m, which is 1 minus a over 2 plus a half, which leaves n as a half minus a over 2. So this is great. Now we can put in a half, or the I of a equals a half times beta of a over 2 plus a half, and a half minus a over 2. Another way that the beta function can be expressed is in terms of the gamma function. So beta mn is equal to gamma m times gamma n over gamma m plus n. So using this is what we have. We have I of a equals a half times gamma of a over 2 plus a half, gamma of half minus a over 2, divided by gamma of a over 2 plus a half minus a over 2. And you can see here that the a over 2's cancel out and the halves add up to 1. So the denominator is just gamma of 1. We know that gamma of 1 is just 1. So now we're left with just the numerator over 2. Now, interestingly here, we can actually use the Euler reflection formula. And what this is gamma z times gamma 1 minus z, just put the little things here, little lines, equals pi over sine pi z. You can actually see that half minus a over 2 is actually just 1 minus a over 2 plus a half. As we said earlier, when we had n equals 1 minus m. So now we can express IA as IA equals a half times pi over sine pi, and here we have a over 2 plus a half. So this is basically our answer for I of a. So we're going to write this a little nicer as pi over 2 times the cosecant of pi over 2 lots of a plus 1. So there we go. Now, what did we have to do as well? So now we have I of a. We want to differentiate that with respect to a and plug in a equals a half. So let's do that. So differentiating on both sides with respect to a leaves us with I prime of a equals, now we still have pi over 2 out the front, and from the chain rule we'll get pi over 2 again when we differentiate, and then we have cosec cot, and that's all negative actually. So pi over 2 a plus 1 cotangent pi over 2 a plus 1. Okay, so this would be minus pi squared over 4 now. Cosec pi over 2 a plus 1 cotangent pi over 2 a plus 1. Okay, lastly, we wanted to plug in a equals a half to get our answer. So we have I of a half equals minus pi squared over 4, and now we have cosec of pi over 2 lots of a half plus 1, which will give us cosec of 3 pi over 4, and the same with the cotangent. And actually evaluating those, we actually get cosec as square root 2 and cotangent as negative 1, which will leave our final answer as pi squared root 2 over 4. And there we go. That's that. That's how we do that pretty wacky, goofy, quirky integral with this sort of variation of Feynman's technique and the beta function. So yeah,